Assistant Professor, Department of ECE, Fdp-Day, Kanchipuram. And the topic for this session is Quantum Machine Learning, Concepts and Frameworks. As a mark of respect and gratitude, we now invite our Principal, Professor Dr. Usha Ishwaran, to felicitate our guest speaker with a short. Along with Principal, I invite our Dean, Mr. Srinivasan, to felicitate our guest speaker with a memento. Thank you, ma'am. Ms.P.Vanitha is Assistant Professor in the Department of Electronics and Communication Engineering at Fdp-Day, Kanchipuram.
Today's resource person. She has done MPhil in physics, an MSc and BSc in physics, and she has a research experience, full-time PhD research scholar at BIT Mesra, Jharkhand, and she was a project associate in the Department of Electrical Engineering, IIT Chennai, hyperspectral data analysis research, semiconductor thin film research, and also she has a training on, she's been giving training on machine learning for physics applications, data science with ML and AI, and also she has teaching experience of quantum computing trainer, quantum computing instructor, as well as machine learning and AI instructor, and she has a lot of technical experience proficient in R programming language for performing impactful exploratory data analysis on diverse business data sets, including bank client data, telecommunication data, and more. She is experienced in leveraging Python libraries such as NumPy, Pandas, PIL, Skillkit, Learn, TensorFlow, and other essential tools to accomplish data manipulation, analysis, and ML objectives with efficiency and accuracy. And she has got a lot of achievements and awards, and she has given a lot of talks and seminars like Introduction to Quantum Hardware at Quantum MIT QML event, and delivered a guest lecture on quantum computing algorithms at Sri Ramakrishna Engineering College, and delivered 3-hour session for undergraduate computer science students on the topic Quantum Algorithm Shaw's Grover's Search and beyond at Sri Ramakrishna Engineering College, Bengaluru. So we welcome you, ma'am, for this today's session.
Good morning, Madam present here. Thank you for inviting me as a guest speaker on the topic of hybrid quantum AI. Okay. So today's topic is quantum machine learning. Especially, I'm going to dive deep into hybrid AI and quantum systems. Right now, I'm working on this hybrid algorithms. Okay. So topics to be explored in this particular event or particular session is, we are going to look into quantum computing fundamentals and what is quantum algorithms. Then from that we are moving into hybrid quantum AI. In that hybrid quantum AI, we are going to particularly look into variational quantum classifier and what are the applications and what are the tools and platforms we need to use to execute particular algorithm. Then what is the procedure of using that particular algorithm. Then we are having a problem statement which is related to medical image analysis. Then our topic will be over. Okay. So what is quantum computing actually? So to understand quantum computing, so we need a help of quantum mechanics plus mathematics, especially linear algebra, plus computer science. We need a programming knowledge, and after knowing everything, we need to apply these things to particular applications, right? So this is not a single application. There are cross-domain applications. We can use it in finance sector, cryptography, calculator, in multiple applications we can use it. Okay. So this is quick recap of quantum computing fundamentals. Okay. So quantum computing is a field that uses quantum mechanics principle, especially those are superposition, entanglement, interference, and it will address the challenges like decoherence also. So what is the superposition here? Superposition is talking about that states which is present simultaneously in both states. For example, in the classical BT we will be using zeros and ones only to code the information, right? So in the quantum mechanics principle, especially the superposition will help us to make the 0 and 1 present simultaneously, which is a unique feature of quantum computing. So entanglement. So another principle is entanglement. So actually this is the topic said by the Einstein as spooky action at distance. That means if you measure one qubit, it will automatically affect the another qubit irrespective of the distance between them. Okay. So it is like sending the information more than the speed of light. That is not possible according to the relativity, right? So that's why Einstein said it is a spooky action at distance. Okay. So even though Einstein helped a lot in quantum mechanics by bringing the photoelectric effect idea and helping us to find the energy of the quantum particles and all, even though his thought is in the classical domain only. That's why he thought that this entanglement is not possible. So it will violate the relativity theory and all. But actually what is entanglement means? There is a high correlation between the two qubits. Okay. So that high correlation decides that if you measure one qubit, you can get the information of the other qubit. It is not like the information transfer through any classical channel or quantum channel. Okay, right. So next, interference. The interference we have studied in our wave phenomenon, especially in the double slit experiments, right? So this interference is the main key for getting the superposition principle. Okay. So decoherence is when the quantum particle is interacting with the environment, it will lose its quantum nature. Quantum behavior will destroy when it is interacting with the environment. Okay. So that is what we are calling it as a decoherence. This is a drawback right now we are facing. That's why we are saying always we are in the disk era quantum computing. Okay. That means this noisy intermediate scale quantum systems that right now we are having, because all the qubits we are preparing is prone to noises, okay, due to this environment disturbance. Right. So we will be calling it as a qubit, right? The qubit is nothing but quantum information. So that is 0, 1 and simultaneously 0 and 1. Okay. So to understand this quantum mechanics or quantum mechanics principle, we need a help of linear algebra, right? In this linear algebra, in the mathematical notation, this quantum state is represented by ket psi. So the symbol is ket psi. Okay. So here we are using different types of qubits. Accordingly, the quantum hardwares are different. Okay. Superconducting qubit is used in IBM quantum computing. Trapped ion qubits, this is different one. Quantum dots, which is giving the different quantum hardware. Photons, neutral qubits. These are the different qubits we are using in quantum computer. Okay. So types of quantum computer. Universal quantum computer. This can be accessed by cloud storage. Okay, that's why it is called as universal quantum computer. So all the gate-based quantum computers are universal quantum computers. Other than that, we are having quantum annihilers also. Okay, right. So postulates of quantum mechanics. Based on this, even whatever the algorithm we are using to our classical data, we have to follow these things. Okay. State postulate. Once everything is given to you, you have to create a quantum state with that. Okay. So quantum state is described by a normalized state vector xi in Hilbert space. This is mathematical point of view, right? So once you get the quantum state, you need to understand what is the property lies in that particular quantum system. Okay. So quantum state in the sense, for example, you can say electron. Okay, if you want to study the properties of the electron, what are the properties available? Spin, energy, momentum, everything. Okay. So once quantum system, that is electron system is made, you want to study its property. So studying that property is called observable postulate. Okay. So observable is nothing but measurable physical quantity. To represent that measurable physical quantity, we are using Hermitian operator. Then measurement postulate. Once you get everything, you want to measure it. So that measurement yields eigenvalues of this operator, which is collapsing the state. Once you do the measurement, your quantum phenomena will destroy and it will turn into classical property. Okay, right. So next, probability postulate. Whatever the measurement outcomes you are getting, that is probabilistic in nature, it is not deterministic. Okay. So for example, in a classical computer, if you want to find a 2 plus 2, it is 4 you will get, right? So this is a deterministic answer. But what the quantum computer will do, if you give the same operation to your quantum computer, it will give 2 plus 2 is 3.9 for some trials, 4.1 for some trials, like that. Okay? So what we are doing, in which maximum trials, in which output you are getting, that is your answer. Let's say if you are getting 4.1, it is rounded up to 4, like that. Okay? So these are probabilistic, not a deterministic one. Then time evolution postulate. So here we can evolve as to quantum state from one time to another time. Okay. So if I want to give a hypothetical situation to understand the time evolution postulate, let's say DNA. DNA is some microscopic particle, but it is a hypothetical situation. Okay. So when you are comparing to other particles, DNA are also little different. So it is a hypothetical. So in 2025, you are understanding the properties of the one DNA. Now you want to know what is the properties of this DNA after 300 years or 1000 years. Okay, that is possible. Now you are in the era of after 1000 years. Let's say you are in 3025. Now you get some properties of that particular DNA. Now you want to know what happened to this particular DNA or what is the property of this particular DNA before 1000 years. That is also possible. Okay. So this kind of time evolution we can done using this quantum mechanics. Okay. Right. So usually to make the quantum algorithms and all, we need this linear algebra, right? So whatever the gate, whatever the circuit we are saying, that can be represented in terms of mathematical operators. Okay. So two operators we will be using. One is quantum gates. In the quantum circuit, the quantum gates available and measurement operator is also available. So what is the difference between quantum gate and measurement operator? This quantum gate will manipulate your quantum state. Whatever the state you have prepared as a gate side, that is manipulated by the quantum states. Whatever the transformation you want to make, you can do it using quantum gates. Once every manipulation is done, you want to measure the properties of that particular quantum system. There you are going to use measurement operators. Okay. So all your quantum gates are unitary gates. Okay, unitary operator. Your measurement operators are Hermitian. Okay. So the operation done by the unitary operator can be reversible. Operation done by the Hermitian operator is irreversible. That means once you made the measurement, your qubit gets destroyed and it will become classical bit. Okay. So this unitary operator will help us evolve over time. Okay. So here dimension of the operator is 2 power n cross 2 power n matrix. This n means the qubits. Okay. If you are having a single qubit system, it is 2 cross 2 matrix necessary to manipulate the quantum system. Okay. Right. So examples for this quantum gates are Hadamard gate, X gate, and Z0 gate. Okay. So measurement operator, poly Z, and projection operator. So even if you are using Quiskit simulator and all, you are measuring it automatically. It will measure. If you give a measurement operator which is having a meter symbol, right? If you use that one, it automatically measures and will give the result, right? So actually it will measure in terms of this poly Z, that is called computational basis. Computational basis in the sense get 0 and get 1. Okay, right. So what is the effect on this quantum state by using quantum gates? It transforms the state unitarily without loss of information. But when measurement operator is operate on the quantum state, it collapses the state to an eigenstate and destroying the quantum behavior that is called superposition. Okay, right. Next, what is quantum algorithm actually? Every quantum circuit, whatever you are making, is called as quantum algorithm. Okay, every quantum circuit is made up of gates, quantum gates, and measurement operator. Okay, these quantum algorithms are implemented as quantum circuit, which are built from quantum gates and typically end with the measurement operation. Okay, so we are having types of quantum algorithms based on different things. Here I classified the algorithm based on hardware usage alone. Okay, based on hardware usage, there are 3 different types of algorithms. One is fully quantum algorithm, then another one is quantum inspired algorithm, then hybrid algorithm. Okay, fully quantum algorithm in the sense it will entirely run on the quantum processing unit. Okay, example, Grover's search algorithm, SARS algorithm, those are the algorithm which entirely run on quantum processing unit. So quantum inspired algorithm means it will use quantum mechanics principles, but it will run on the classical simulators only. Okay, so those kind of algorithms are quantum inspired algorithm. Even though here I am talking about a hybrid classical quantum algorithm, since I don't have access to use the quantum hardware, so I'm just going to simulate through classical computer only. Okay, so next one, hybrid classical quantum algorithm. That means we are using classical computers also, quantum computers also. Okay, the portion of the work is different. Suppose for optimization I want to do, I will do it in the classical computer. If I want to do the measurement, I will do it in the quantum computing. Okay, if I am using classical computer and quantum computer together, that is called hybrid classical quantum algorithms. Okay, right. Now we are moving into hybrid quantum AI. This is a subset of QML. Okay, quantum machine learning. So this is quantum machine learning or hybrid quantum AI is a field that combines quantum computing and classical machine learning. Okay. So why we needed this one, even though we are having many advantages and technical advancements in machine learning. So when we are using this machine learning continuously, that means like we are using deep layers, deep neural networks to understand the patterns lying in the data. So it started creating hyperlocal variables. Okay, that means latent variable gets increased. When the latent variable gets increased, the data space reaches to high dimensional. Okay, so in that case we will be reaching this cause of dimensionality. So that means if you want to know the intrigue patterns of the data, relationship between the 2 data points, your latent variable will get increased. It will increase the data space. So in that case, your classical computer will struggle to handle that thing. So our quantum mechanics principles by using this quantum machine learning algorithms will solve that thing. Okay? Right. So hybrid classical quantum approach integrates the learning strengths of classical ML with the quantum ability to handle high dimensional data, helping to overcome the practical limitations of today's hardware. Okay. So in this architecture, classical components can handle tasks like data preprocessing, feature extraction, and classical optimization. So what about the quantum components? Quantum components feature mapping, optimization, or exploring high-dimensional Hilbert space. Okay, right. So we are having different types of hybrid quantum AI models: variational quantum classifier, variational quantum eigensolver, QAOE, quantum support functions, and more. So in this, we are going to see one algorithm, that is variational quantum classifier. Okay. So this variational quantum classifier uses parameterized quantum circuits to learn from and classify data. Okay. So classifier in the sense it is used for classification purpose. Okay. Circuit parameters are tuned using classical optimization algorithm to minimize the loss function for a classification task. Okay. So what actually this VQC will do? We are having input data. Let's say we are going to explore some medical imaging data. In that we are going to delineate brain cancer, whether it is healthy tissue or cancer tissue or a blood pressure or like that. Okay. So in that case, I just want to do the classification. So I am taking the classical data. So after getting the classical data, our first step is whatever the format you are having, it should be converted into numerical form. Okay. Once it is changed into numerical form, you have to import that into quantum state. This is called quantum state preparation, we will be calling. Okay. So we are applying parameterized quantum gates to this quantum state. Okay. So after that, we will be putting measurement operator and we are measuring the result. This measurement result is given to classical optimizer. The classical optimizer will do the optimization and will update the whatever the parameter it is giving to again to that parameterized quantum circuit. Okay. So this is how the process is repeating and we are getting the final result. Okay. So this is same as the machine learning thing, right? So input layer, hidden layer and output layer is available, right? So in the hidden layer all the training will be happening, then output layer measures, and if the cost function is not reduced further, then the process will be repeating, right? The same way, here instead of hidden layer, we are using this quantum circuit. Okay? Right. So this is a figure of variational quantum classifier. We are having data set. We need to do the pre-processing steps to use it for our particular application. Actually, I told you, right, we are using medical image data. It is in an image format. I want to do all the pre-processing and convert it to the numerical data form. Let's say I am taking it as CSV file or data frame. Okay. So now this data is mapped into quantum circuit or quantum state. So after that, we are feeding this particular state to variational circuit which contains the parameter. So this is measured. Measurement gives the classical value that is given to optimizer. Optimizer will check the loss function and update the value again to the variational circuit. Okay, this process continues and then we will get the optimal solution. Right. So again the same thing. So if you want to use this hybrid models for any of your problem statement, these all the steps need to be followed. First one, you need to do the pre-processing thing. Okay, and do feature extraction. That means the data whatever I have taken, it has around 1000 columns. Okay, I am feeding this particular data to the quantum hardware. Okay, so I should not put as it is. I just want to refine my data before I am feeding into it. So all the 1000 columns are not necessary. So I can use some reduction algorithm like PCA to reduce that particular features. Okay. So this is called feature regression. This is normally done by classical algorithm. Then quantum state preparation. So once the quantum state is prepared, then you are doing the encoding part. That means classical data is feeding into the quantum state. So once it is done, you are doing the measurement. Then you are making the optimization on the measurement result. Then it is repeating. The final result is giving your optimal solution. Then you are doing the classical evaluation. That's it. Okay. The same structure as this one. Okay. So here also you are having classical data. Wherever you are having this quantum state means your classical data is encoded into quantum state. Okay. So how this classical data can be encoded into quantum state? So we are having different encoding methods: angle encoding, basis encoding, amplitude encoding. We are using appropriate encoding method method to encode our classical data into quantum data. Okay, once it is done, we are passing it to the parameterized quantum circuit. There our parameter will be optimized. Okay, we are measuring it. That measurement result is again given to classical optimization. Then that parameter is again updated to the parameterized quantum circuit. Then we are checking for the optimal solution. So once optimal solution is reached, then we will stop our algorithm. Okay, right. Okay. So this is again the brief of what is happening in each step. Okay, the pre-processing and feature extraction. What are the things you need to do? You need to clean the data, normalize the data, and structure the raw data. Okay, and extract only relevant features to reduce dimensionality and improve interpretability. Okay. Next, quantum state preparation. In this, you are encoding classical data into quantum state. For that, you are using the techniques like amplitude encoding, angle encoding, or basis encoding. Still, we are having n number of encoding methods, but these are the popular ones we are using, right? So, quantum processing using quantum. So, we are applying quantum operations to manipulate or extract patterns from the encoded data. So, this is the work of quantum gates here. Okay. For that, we are using entanglement, interference, and unitary transformation. Okay. Then optimization. We are getting some measurement result from this first step. Then we are optimizing it using classical optimizer like gradient descent or Cobila. Then again we are feeding it to the your parameterized quantum circuit. Then final measurement will give you the exact solution whatever you want. Okay. So classical post-processing and evaluation means you are analyzing the result and comparing whether your model is performing well or not. Okay. Right. So this hybrid quantum classical machine learning algorithms are used in various applications like protein folding problem or molecular simulation, materials optimization, drug discovery, fraud reduction, medical image analysis, supply chain optimization, and other. That means it covers all the domains. Okay. So to make this hybrid algorithms possible, we need some tools and platforms. If you are using IBM quantum hardware, you need to use Qiskit. This is open source software development kit. If you are using Google, then TensorFlow Quantum. This is an open source library. If you are using Xanadu, you can use Pennyline. Even whatever the algorithms you are making, you can try with this Pennyline. Okay. So SIP, this is also Google product. This is a Python framework. It contains circuit simulator also. Okay. Right. So another one, Torch Quantum. This is PyTorch based. This is also open source library built on PyTorch. Okay. Which platform is comfortable for you? You can choose that one. So same procedure. This is what we are going to use for our problem statement. So that's why I am revising it again. Okay. So for our problem, my data set is image data set. Okay. So I am loading the data first. Second, pre-processing the data. What I am doing, I am converting the images into feature vectors. It's in terms of numerical data. I am converting it into the form of data frame. Then I am normalizing the data. Normalizing the data means one data value contains 0.1 like that. In another column, their value will be in the thousands or 10,000. In another column, it is like 1 lakh like that. Okay. So if I am giving the data in this way, which is the highest value will be given first preference, and your process will be biased to that particular feature. Okay. So to avoid that, we will be normalizing it to particular range from 0 to 1. Okay. Then reduce dimensionality using PCA, principal component analysis. Okay, I told you right, I am having 1000 features in my data set. Okay, all the 1000 are not necessary. So I am reducing it by using PCA. Right. So then once everything is ready, my data set is ready. Now I am splitting the data set into training and test set. Okay. So I need to define quantum feature map. Feature map is which encoding method I am choosing, whether angle encoding or amplitude encoding or basis encoding or not. Okay. So if you are choosing this encoding methods, this depends upon or it costs the number of qubits also. Okay. If you are using basis encoding, you will need more qubits. Like let's say your binary value is 101. So for 1 there is 1 qubit, 0 for to store the 0 you need a 1 qubit, for 1 you need another qubit. It's like a 3 binary value, you need 3 qubits. Okay? Right. If you are using angle encoding, similarly, if you are using 200 features, for each feature you need a 1 qubit like that. Okay? So if you are using amplitude encoding, it is a good thing. You can use 2 power n qubits only. That n represents the qubit. 2 power n is your feature. Okay? For 200 features, you can use 8 qubits only. Okay? But the problem is the amplitude encoding needs manual construction of the feature map. Okay? So that's why we are sticking into the angle encoding. Okay? Right. So then we are defining our recreational quantum circuit, which is nothing but the combination of quantum circuit and measurement operation, like quantum gates. Okay, quantum gates and measurement operators. Okay. Then we are initializing our hybrid classifier. For our problem, we are using Cobila. Then we are training the model using training data, then predicting the labels for test data, and evaluating the performance and interpreting the results. Okay, right. So our problem statement is we are delineating the brain cancer using this hybrid DQC. Okay. So one more thing I want to tell you here, this data is not a normal MRI data or other things. It's a HSI data. HSI data in the sense hyperspectral image data. Okay. So it is captured by the hyperspectral camera. So that hyperspectral image means you will be having voxel in every 3D image, right? So if you see 2 dimension, it will be pixel. Each pixel contains a particular intensity or brightness value, right? So when you are seeing this HSI data, it is a 3D cube. Okay, in one cube, you will be having thousands of spectral signatures, spectral bands. Okay, if you are talking about the RGB, red is one color, red is one band, green is one band, blue is one band. In one pixel, you will be having 3 bands only. Okay, whatever the normal camera is capturing is the RGB image. Okay, it will contain 3 bands. Okay, so HSI will contain around 100 to 1000 bands in one pixel. Okay, so the dimension of the data set is high when you are training the data set. Okay. So why we need this means, you know that, right? If you are seeing the ceiling with this particular color, it is reflecting that particular light only, right? The remaining colors are observed. If you are seeing the sofa in the red color, it is reflecting the red color. The remaining colors are observed, right? White light contains 7 colors, you know, right? In that, it just reflects the red color and observes all the colors, right? Similarly, when you are capturing your brain with this hyperspectral camera, normal tissue will observe particular bands and reflect particular bands. Cancer tissue will observe particular bands and reflect particular bands. Okay, so that means the spectral bands are different for normal tissue and different for cancer tissue. Okay, this is like spectral signature. Like we are having a fingerprint in our hand, right? So this fingerprint means my fingerprint means myself only, right? Your fingerprint means yourself only. Like that, this spectral bands, 100 to thousands of spectral bands create a fingerprint for that particular tissues. Cancer tissue has some fingerprint and normal tissue has some fingerprint, like that. Okay, so we will be calling it as a spectral signature. Okay. Each tissue has its own spectral signature. Okay, so if you want to reset the cancer tissue from your brain, you should not touch the normal tissue, right? Because brain is not like a normal part. If you extract or reset extra normal tissue from your body, your body's complete every activity will happen, right? So that's why resetting that particular cancer tissue is very much needed. Okay, so for that we are using this hyperspectral data is normal tissue like that. So that's why we are using hyperspectral data here. Okay, one more disadvantage of this hyperspectral, it is a high dimensional data. So when it is having high dimensional data, we need to find out the relationship between the features accurately, right? So this quantum circuit is very much helpful when we are handling this much of data. Okay. So I took this raw HSI image data. I am doing the pre-processing thing. So all the HSI images, the hyperspectral image is not stored as our normal RGB image. It will be stored in a different format. Okay, HDR format, raw.hdr format. Okay. So I just want to open it through Python libraries and want to make it to the usable format, that is like a numerical data format. Okay. So that is what I have done in pre-processing. Then feature extraction. I told you, right? In particular pixel, it is around thousands of bands. I don't want all the thousands of bands. I just reduce the 1000 bands to 200. Okay, or less than that. That's your choice. Okay. Once I have done that, I am using quantum encoding. I am using Z as a feature map. This is one of the angle encoding technique. I told you, right, why I am using this angle encoding. Even the amplitude encoding allows smaller number of qubits because we need to construct manually. Okay, that feature map circuit should be constructed manually. So here this is a Z feature map is available in Qiskit library, so I can directly use it. Okay. So then I am just feeding it to the parameterized circuit, that is variational circuit. Then after that I am doing the measurement. That measurement result is given to the classical optimizer to look for the loss function. Okay. Once the loss function is reduced, we will be getting our final result, or otherwise it is again given to the variational circuit. Okay. So the final classifier output tells about whether our model is predicting correctly or not, accurately or not. Okay. Right. So I will show you that coding part. Do you have any doubts so far? Anybody? Then I will ask you a question from whatever I said so far. Okay? Simple questions. Okay, what are the quantum mechanics principles needed for this quantum computing task? Anyone? Qubit is quantum information. To create a qubit or represent a quantum system, what are the important quantum mechanics principles are needed? Yes, superposition, right? So, if you're having any single state, like let's say get 0, so whatever the quantum circuit you are making, your default state is gate 0, just a 2 cross 1 column vector. Okay, you cannot use that gate 0, the 2 cross 1 column vector for your entire operation, right? So you want to create your quantum state by using that gate 0. Okay, for that we are using superposition idea. Okay, so for using superposition we are using head-on gate. Okay, so head-on gate can connect any number of basis states together, okay, with this interference concept. That means there is a phase difference between states whatever we are using. Okay, I don't think you are getting what I am saying. This is the hybrid PQC code created using Python, and we are using Qiskit framework. So this is the actual data. Okay. So it is created by hyperspectral image, right? So in this I'm having just 36 images, okay? But the total memory of this particular 36 image is around 60 GB, okay? So this is not possible to handle by the classical computer when I'm giving the entire data. Even for my this thing, I used only one image file, okay? So more than that, even the free GPU cannot allow, okay? Right. So if you see here, this is my RGB image, this is my brain data, okay? Actually, this brain data is captured by the hyperspectral camera and marked by experts from this field, like doctors and lab technicians. Everyone sit together and just identified which is cancer, which is a normal tissue, like that. They use some other encoding technique like spectral angle mapper. From that, they change it to this HDR file, okay? And this is how they delineated it. That means they segregated it. For the same image, whatever I am showing, where you are seeing this red color, this is the cancer tissue. Okay? Wherever you are finding green color, it is a normal tissue. That blue and all blood vessels. Okay? If you see this particular image, only I just focusing on this area and this area only. Even all the white things are not necessary for my data, right? So this is why the pre-processing step is very much important. Okay, this all unneeded data points are called as sparse data that will be removed automatically through our pre-processing steps. Okay, right. So this is our problem statement. Brain cancer delineation using hybrid PQC. I am just using both classical part and the quantum part together, right? So first I have done the same thing with the classical algorithm, SVM, support vector machine. Then I move on to quantum PQC. Okay. So this is the details of my data set. The raw original data which contains around 826 band. Okay. In single pixel you are having 826 band. Okay. That is stored in raw and raw.htr file. Okay. So this raw file actually has binary values of that pixel values, and raw.htr file contains the metadata. Okay. It will help you how to read this first raw file. Okay. And we are having in that file, okay, dark and white references for calibration process. Okay. So that is done by the camera. That means we are setting up the camera before taking the image. That file also available in that particular folder. And ground truth map. That means ground truth contains labels. Other one contains all the features. Okay. So label in the sense which part it contains the cancer, which part it contains the normal tissue, like that. Okay. So totally we are having 4 classes here. One is normal tissue, another one is tumor tissue, another one is hypervascularized tissue, and fourth one is background. This background are not needed. Okay. So actually this particular thing is called HS cube. Okay. For that I am using Python spectral library because it is stored in the NV format. So I need to use Python spectral library. So I am installing it. This is a step to install the libraries in Python. So I am also using this Qiskit framework, right? So I installed that one also. We will install Qiskit machine learning. So spectral libraries to handle the spectral data, everything imported here. So I am loading the HSI data. These are the normal Python keywords to open the data and unload the data. Okay. So this is how my input looks. Okay. So I just used random images here. So similarly, I have loaded my ground truth data, that means it contains labels, right? So it will look like this. In this image, this yellow color part is my tumor part. Wherever I am getting yellow color, that is tumor. Okay. So that is the image one. I just visualized it or what is happening in the image. I understood that. Then I am just moving on to convert it to numerical format, just as CSV format, Excel file format. Okay. So these are the steps to create Excel format. So this is how my data looks like. Okay. Actually, look at here. How many rows are I having? Even for few images. Okay. Can you see here? It contains 826 columns and around 11 lakhs rows. Okay. Right. So that's why it needs to be pre-processed. I'm just removing all the parse value like background values here with this step. Okay. Then I'm just segregating what is input, what is my output separately. Okay. So after that, my samples are reduced to 58,000. It was initially 11 lakhs, now it is converted to 58,000. Okay. So once it is done, I want to normalize my data. Normalize my data in the sense I want to do it within a range. Okay. So you can see here, minimum value is 1 here, maximum value is 4 here. Okay. So everything should be in the one range, that is 0 to 1. Okay. So that we have done using this min-max scaler. Then I am applying this principal component analysis to reduce my dimensionality. Okay. Initially it is 826. Now I have reduced it to 200. Okay. So it is converted to 200. So now I am having this many rows and this many columns. So after my data set is ready, I am splitting it into training and test set. Then applying SVM, then I am applying hybrid accuracy. So here I am using the scikit-learn, sklearn library and Qiskit machine learning libraries. Okay. So this is the step where I have applied SVM. This is how it classifies. So background classifies as it is currently. Hypervascular tissue, it is classified as correct. Okay. Only few are wrong. Okay. So actually this is a single image for this SVM, right? So that's why it has done very well. Okay. So if I feed all the 36 images, then definitely maybe the accuracy will vary. Okay. It's just for explaining part. Okay. I haven't done it with the real GPU. I have done it with whatever available with this collab. Okay. So this is my report. So precision is around 99%, recall is around 199%. Okay. So actually SVM is working very well here. So these are the different visualization techniques. Okay, not only the data, the output also can be visualized using different methods. Confusion matrix, classification report, or heat map like this. Okay. So then we are moving into hybrid VQC. Here I am just giving all my input data, and especially I put 1 in this. Okay, actually it means the columns. Okay, whatever the columns I am having, that is going to be number of qubits. So I took 200 columns, right? So it will be taking it as a 200 qubits. Okay. So feature map, once everything is ready, the classical data is ready, it should be encoded into quantum circuit, right? For that I am using the ZZ feature map. Okay. This is nothing but the angle encoding. Okay. So whatever the data value is present in that column, in the 200 columns, that value is taken as an angle. Okay, theta value. Okay. So accordingly, it will encode its data. Then unsatz, it's a real amplitude, whatever I have written is just nothing but the variational circuit. It contains the quantum gates and measurement operator. Okay. Then after my quantum circuit is ready, I want a classical optimizer, that is Cobaila. I have used that. Cobaila is nothing but constraint optimization by linear approximation. Okay. So here also I haven't used a real quantum hardware. I used a simulator. That simulator is called sampler. This is available with this Qiskit primitive. Okay. So if I run it, how my feature map looks like, it will show. Okay. So for that I need to run the entire code from the beginning, from the data set loading. Okay. Then I created a VQC. VQC is a combination of the angle encoding steps, ansatz, and whatever the optimizer I am using, and the sampler. Sampler is used for simulating my circuit. Okay. The simulator is, instead of quantum hardware, we are just checking with the classical simulator. Here I am using classical simulator. Okay. So last is calculated by cross entropy. Okay. So if you run this, it will train on this particular data and will give the output. That output results, the predicted result we can get here. Okay. So this is how we are executing our hybrid VQC. So do you have any doubts so far? Everything is written in Python. Simulator. No, ma'am. If I want to do it, I have to run from the beginning. It will take time. If you want, I will share this code with you and the data also with you. You can try in your system. Any doubts so far?
Participants can go for a break and you are requested to gather back at the hall by 11:10.
Session conclusion. So actually we are using hybrid architecture, right? Why we need to use this one? To leverage the both strength of classical and quantum support, right? So right now, whatever the quantum we are talking about, it is in the development state. Okay. So whatever the quantum hardware it is available, even though we are having n number of qubits, not n number of qubits, around thousands of qubits are available for encoding purpose, but not all the 1000 qubits are useful here. Okay, definitely when you are creating a quantum state by using those qubits, in between the process, there is lot of chance to disturb that particular quantum behavior of that quantum state that we prepare. Okay, so this kind of device is actually called as a disk-error device. Okay, for handling these devices, this hybrid classical architecture is very much helpful. Okay, so as I told you, this hybrid model is successfully useful in different applications. So like binary classification. So whatever the example I have taken is one of the multi-class classification only. Okay. So it improves generalization, optimization tasks, and copyright detection, NLP tasks, time series analysis. So in all the cases, we can use this hybrid approach successfully. Okay. So when I start this hybrid approach, I told you that when there is a curse of dimensionality, we can use this hybrid approach to resolve that issue, right? So one more biggest benefit is, even if you are having small training data set, this hybrid approach gives the optimal result. Okay, when you are using this small data set in classical machine learning algorithm, definitely you will face the problems like underfitting and overfitting, right? So that means your model will start memorizing the data instead of getting training and instead of getting the information from the data. It start memorizing the data, and when you are giving the test data, what it will do? It will do this overfitting and underfitting issue. Okay, overfitting and underfitting in the sense it won't perform well or it will perform very well. Okay, so this will happen in this small data set. Okay. But this hybrid approach can be useful for the small data set also. Okay, so those are the papers I have given here. Okay, you can refer it. So if you are using classical algorithms and you are facing this data set issue, like you don't have much data for your particular problem statement, you can try this hybrid approach for that data set and check your accuracy with this one and that one also. Okay, so that's all. These are the reference for that special papers. Okay, if you want, I'll share this PPT with you. Okay, right. So that's all. Do you have any queries? Okay, so what framework we are using is Metas here. Okay, whether you are running in IBM Quantum hardware or Google or Xanadu or like that. Okay, so if you there is lot of disadvantages as well as advantages for each computer. Okay, if you are using Xanadu, what happens? There is less noise prone. Okay, Xanadu is made up of this ND diamond atoms. It is not easily destructible by the environment issue. Okay. But the problem is, still it is developed to 6 qubits, not more than that. So if you come to the IBM, we are using superconducting qubits. We reached around 1024, but we are not able to use all the 1024 successfully. Okay, that is the issue with this thing. Okay, so first thing, which platform you want to use? Okay, so we are using IBM this biscuit commonly, right? Because it is available through this cloud storage, and so far they have given us a free access. Okay, so but right now for last 1.5 months they are charging for that also. Okay, so even though you don't go for quantum hardware, you can use the simulators. So there are keywords you can. In my example, I have used this thing, right? So when I am running, that means when I am defining my circuit itself, I used this keyword sampler, right? So what it means, actually it is a local simulator. It can handle 25 to 30 qubits practically. Okay, so we can use the simulators in this way using keyboard also, or you can use some other discrete simulators by calling it as a backend simulator. Okay. And one more thing, so whatever we want to try, this is already available with the documentation. If the question is providing that one because it is new to all the users, right? It is providing the documentation properly, that means with the example and how to use it and example code, everything. Okay, they are trying with the data set also and what is the example code also, like that. Okay. So this is one simulator. Okay, cookie dance simulator. So how to use this one? They have given all the things. How to simulate through the code also. Okay. As I typed, you can also type what is the cookie simulators. Okay, they will give the all the procedures how to use it, like that. Yes, sir? Everything, yes. So that's why I am saying that applying for our data set is very easy. Only thing we need to know how to prepare the data set and how to bring that into the quantum encoding part. Okay, how to convert this classical data into quantum state. That is the main thing we need to focus on. Remaining thing already available, we can practice through it. Once we have practiced through it, when this fault tolerant error is achieved, we can create our own algorithms accordingly. Okay. So one more simulator famously used in Quantum simulator is here. Okay. So they have given what is the advantage and disadvantage of each simulator. Okay, you can check it like that and you can use it. Okay. So you don't want to call anything, you can use sampler kind of thing. Okay. Yeah. So any other doubt? These are the whatever I showed, right? This is a common one we using as simulator and quantum simulator. How to converting the classical state into quantum state. Okay. Can I get board and pen? So actually, before I am explaining everything, I have explained you how it is explained mathematically, right? Then we have move on to the further thing, okay? So mathematically, every quantum state is represented using this gate set, right? Gate set, right? So in this, all the information about your system is available. Let's say there is a single qubit, okay? It is written like this. So now I am having data frames. Okay. Now this data frame, it is a classical data. Let's say It contains rows and columns. Okay, now I am going to feed that into this form. Okay, so my main task is how I am creating this one. Okay, so for that I am using the circuit called variational circuit. Okay, so variational circuit actually this is also created by using the help of quantum mechanics principle. The principle is called variational principle. Okay, so what actually we will do this in this variational principle, we need to find the let's say any atom, hydrogen atom. Okay, it contains single electron. There is no issue with it to find the energy of the single electron. Okay, suppose it is combination of multiple electrons. Let's say helium. Okay, helium atom contains 2 electrons. When the number of electrons is increasing, it is difficult to find the ground state energy. Okay, so in that case, according to the variation principle, what they are doing, they are taking some trial wave function. Okay, trial wave function in the sense they are guessing certain wave function for that particular helium atom. Okay, and they are measuring energy measurement on this particular system, and they are getting some energy. Okay, this is for the trial wave function. Okay, this is always little bit greater than the original ground state energy of the helium atom, like that. Okay, so what is the concept they have taken here? The trial wave function they are creating, right? So that concept they have taken here. Okay, so in this variational circuit, we are creating one trial wave function like this. That trial wave function we are calling it as a quantum state. Okay, so through the variational circuit, we are creating this one. Now I have created this one. Okay, so how I can create this one? So I'm just giving the simple one. I told you, right, whatever the default quantum base states available is 0. Okay, now I'm having this one. Okay, so now I want to create this kind of state. Okay, so what I can easily do, I can apply Hadamard on it. Okay, if I apply Hadamard on it, what I will get? It will give superposition of this. Okay, so with this, you will get some combination of the states like this. Okay, so I just used the Hadamard. It will give the rotation like this. Okay, so Hadamard always give the even superposition like this. This is having 50% superposition. This is having 50% superposition. Okay, so if you want to arbitrary superposition like this. Okay, so what you can do, instead of Hadamard, you can use any rotational operator, rotational gate. Okay, you can use any rotational gate to create this one. Okay, so in the rotational gate, what is your parameter? The theta is your parameter, right? So as per the theta value, it will create its own state. Okay, so what I am saying here, this theta whatever you are giving is your value, this feature value. Okay, so this is how we need to do it. Okay, so in the example I have shown, right? Here I have shown, right?
Amen.
So look at here, is a feature map I am using here, right? Whatever I told you, right? I have explained it to you manually, right? So when I am using this one, it will do automatically. Okay, it will do the encoding. That means it might have some quantum circuits like that. Okay, so if you draw that by using this function, you will get it. Okay, or otherwise, I will show you. for everything the documentation is available. Okay, it will show what is the circuit also, the IBM quantum platform documentation. So can you see here? It will be like this. Okay, whatever the value it is mentioned is our theta value. Okay, so somehow I want to achieve that psi state with the superposition of basis states. Okay. Okay. So psi is written as alpha 0 plus beta 1. Okay. Actually, this is what basis state I mean. Okay. This is according to the number of qubits you are choosing. Okay. Suppose you are choosing single qubit. Single qubit means dimension of the spaces or number of bases is decided by this formula 2 power n. If you are using single qubit, 2 power 1 is 2. So you are having 2. 1 0, another one is 1. Okay, this is also based on quantum mechanics principle. Okay, every quantum system is a two-level system. For example, if you take electron and you are studying the properties of the spin, it has two levels of spin. One is upspin, another one is downspin. That upspin is taken as a 0, downspin is taken as a 1. Okay, so why we are using 0 and 1? It is a conventional. When we are developing the quantum theory, using 0 and 1 is very easy to go forward. Okay, so that's why I am sticking to 0 and 1 only. Okay, so suppose you are using 2 qubit, the possible states available is 4 here. Okay, so this is related to the classical bits only. If you are having 2 bits, what is the possibilities? 0 0, 0 1, 1 0, 1 1, right? So same way, this one will become alpha 0 0 plus beta 0 1 plus gamma 1 0 plus delta 1 1, like this. Okay, so when the number of qubits increasing, the number of basis states also increasing. Okay, so that number of basis states connected with each other according to the theta value. Okay, that is what we are saying phase. In the superposition also we are saying that one only, right? So that means if it is in the superposition state, there is an interference between this state and this state, right? Yeah. So when number of qubits increasing, we are getting this many states. So that means my angle is encoded in this accordingly. Okay, got it? So I have said the remaining thing also, basis encoding, right? So basic encoding in the sense I am coding my information in this. Okay. So one more thing I have said, amplitude encoding. So these are my amplitude. Alpha, beta, gamma, delta is my amplitude. Okay. My information is stored in that alpha, beta, gamma. Okay. So here it is done by angle encoding, done by the rotational operator. That means there is a phase difference between the different basis states. Okay? Right. So if you see this circuit, there are the values given here. This is my data point value. Okay? This P operator also rotational operator. Okay? So this is how you can repeat your structure. Okay? Right. So you got it right, what I want to say. How we are doing the encoding thing. Okay. So we can use amplitude encoding also. In that what we will require, comparing to other things, using minimum number of qubits will increase our accuracy, right? Right now, whatever the simulator is available, right? So, if you are using amplitude encoding, if you are having 200 features, 2 power n will decide your 200 features. Okay, let's say 2 power 8. What is the 2 power 8? It is 32 into to consider it. What you will get? Correct? Second, tell me what is 2 power 8? One zero two four. Okay. So what is 2 power 7? 2 power 6. That means I want a value which is near to 200. More than that, 138 you will get for how many? 128 for 2 power 7. Okay, so that means this 200 lies between 2 power 7 and 2 power 8. So that this 8, this n decides the number of qubits. Okay, so you can use 8 qubits alone to encode the information. Okay, so in that case, what you want to do, instead of using this ZSL feature and circuit directly from the QC library, you can create your own circuit in this way. Okay, you can check mathematically and you can put that into the simulator and what is the result it is giving. Accordingly, you can fine tune that particular circuit. Okay, but same idea. Okay. Any other doubts? So right now, you just want to know what you want to do. Then every documentation, every source is available actually. Any other doubt?